turn that off. Are we back? Sorry about that. Can you hear me again? Okay. Thank you. Anyway, I don't know why it does that sometimes. Anyway, so we have our table, and that will allow us to calculate this T alpha over 2 value from the table, as we just saw. And that will let us calculate our margin of error based on that. So overall, once we find our margin of error, then our confidence interval will be x bar minus our margin of error to x bar plus the margin of error. Now we can write that in one of two ways. We can either say x bar minus e comma x bar plus e, as this would be an interval notation. Sorry about that. Yeah, I just realized that. Or we could say x bar minus e is less than mu is less than x bar plus e. And that's with inequality notation. So either of those is acceptable. I put the interval notation on the formula sheet, but we could do it either way. So we'll be given the x bar value. So we really just have to focus on calculating this e value, this margin of error that we've been talking about. And that will allow us to find our confidence interval based on that. Okay. Now, the other question that is we typically have at this point is, how do we know which margin of error to use? Whether we have, are we given sigma or are we not given sigma? Well, this will usually be given, or will be informed of this by the way that it's stated in the paragraph that describes this situation we're working with. It'll either say specifically it's the population standard deviation or the sample standard deviation. And if it doesn't specify, we should always assume it to be the sample. So we would always work with this this second method unless it specifically says population standard deviation. Then we can use the other one. I might give you one of each, since we're going to do two of these on the both the review and the test. I don't know if I gave you one of each on the review, now that I think about it. I may have given you two of the same kind, but I'll probably make it, I can double check right now, actually. Just one second. sample population. Yeah, I gave you one of each. Good. All right. So, yeah, I gave you one of each, where one is, you're told it's a population standard deviation, and in the second problem, you're told it's a sample standard deviation. And so we'll have one of each where you find the margin of error one way, and then another where we find the margin of error another way. Now I'll do the same thing on the exam. Alright, let's do some of these now. Now that we've talked about how we do the problem, let's do the problems. Let me come up with an example. This one's just a generic question, but the idea is there. And when we get to it, we'll do a couple of actual word problems where we have a kind of situation described. Let's suppose that a simple random sample of size 40 is drawn from population that has standard deviation let's say our standard deviation is 10. If we find our sample mean is 85, calculate the following. A, we want a 90% confidence interval, and we'll start with that. Alright, now we know our sample is size 40, so you know n is 40. It's drawn from a population that has a standard deviation 10, so that's a population standard deviation, and it's important that we know that this is sigma equals 10, so we are working with a population value, and we have a sample mean x bar of 85, and we have 90% confidence. So z alpha over 2 let's see, bring that up again just for my sanity's sake. Okay. Now, if we have 90% confidence and we actually know the value of sigma, remember what we said over here. This is sigma is known, so we know that our error term is going to be based on z alpha over 2 times sigma divided by square root of n. And for 90%, z alpha over 2 is 1.645. So we'll write that down. But now we write the error term like I just showed you. Z alpha over 2 times sigma divided by the square root of n. So it'll be 1.645 times 10 divided by the square root of 40. Okay. So we just want to calculate that. 1.645 times 10 and divided by the square root of 40. Close parentheses. And so we get a value of, looks like about 2.6. 2.6 would be a good estimate there. Okay. So our error term is 2.6. Now, x bar is 85, so our confidence interval we know is x bar minus e, comma, x bar plus e. So in this case, we'll get 85 minus 2.6 and 85 plus 2.6. And so working that out, that would be 82.4, comma, 87.4. Okay, so we can say, we'd like to summarize this with a sentence also, that's important. And it doesn't have to be real lengthy, just something that addresses what we're trying to find. So we can say with 90% confidence oh, thank you, Deviation. I don't know where I got hung up in that last four. Yes. So we can say with 90% confidence that the population mean is between 82.4 and 87.6. Okay, and we do want to write a summary statement there. All right. So what I might do in the exam is I'll split this up into two questions. First question I'll have you go through and like identify n, sigma, x bar, z alpha over 2, and then e. Just fill in the blank basically. In the second half, our second question, have you give the confidence interval and then write a summary statement, and that'll be like a short answer. It'll just be it's set up as an essay question, but you don't have to write an essay, of course. Just writing out the confidence interval and the sentence summary is all we really need for that second part. And I'll be sure to indicate it as such in the instructions. So that'll be open ended, and I'll just have to grade it manually. All right. Any questions on how we arrived at this, though? Okay. Let us continue. So that was problem A. We want to construct a 90% confidence interval. So problem B, let's construct a 95% confidence interval. Okay, so we still know that n is equal to 40, sigma is still 10, x bar is still 85. That information hasn't changed. Now we have 95% confidence, which tells us that z alpha over 2, that will be equal to 1.96. And again, we just looked that up on our formula sheet, which will be included in the instructions for the test at the top. Alright, so that gives us z alpha over 2, so now we can calculate our error term e, which is z alpha over 2 times sigma divided by square root of n. So 1.96 times 10 divided by square root of 40. And so for that, I think we can round it to 3.1. Now, when we approximate our error term, this is a little bit different than what we've said previously. Previously we've gone, okay, 3 or 4 decimal places is fine. For our error terms here, if we have whole number data for like x bar, like we have here, we should either round to the nearest whole number or to just to the first decimal place. We don't want to go any further than that because it may not have any context in the world of that whatever value this represents in this case. For instance, either on the review or the test, there's a confidence interval problem involving money. So in that case, our error term would ideally be rounded to 2 decimal places, since we are talking about a dollar amount or monetary amount. So in some cases, the data will lend itself to a certain level of rounding that makes more sense than other values. But otherwise, I would just go, if this is whole numbers, we can go to the nearest tenth. This is 1 extra decimal place, or 1 extra place after wherever the original data ends. So that one's a little bit, I'm not going to be as strict on that, but that's kind of the foundation there. So. or that's the reasoning there, I guess. It's a better way of saying it. So now we want to create our confidence interval. So we'll take x bar minus e and x bar plus e. So we'll have 85 minus 3.1 and 85 plus 3.1. So this is 81.9. This is 88.1. So now we can say we are 95% confident that the population mean is between 81.9 and 88.1. Okay. Now, let's look at those two summary sentences we just wrote. This one and that one. With 90% confidence, we said it was between these two values. And with 95% confidence, we said it was with these two values. That means that by increasing the level of confidence from 90 to 95, we went from two numbers that were closer together to two numbers that are further apart. Well, it turns out if we want to have a higher level of confidence, we're going to have a bigger interval of values that it could possibly be. So this gives us kind of a more narrow range of values, but we're not as confident. Whereas here, if we want to be more confident, it gives us a broader range of values. And that's generally what's going to happen. If we increase the level of confidence, then we're going to increase the interval in size. Basically, what's happening is the margin of error gets larger for a higher level of confidence. Okay. Because in this first one, our margin of error was 2.6. Okay. And the second one, with the higher level of confidence, we had a margin of error of 3.1. And that difference between the two is entirely contained in that level of confidence. Okay. Right. Let's look at a problem where sigma is unknown. Simple random sample of size 40 has a sample mean (85) and standard deviation 10. Create a 95% confidence interval for the mean, for mu. Now, I've actually given us the same data this time, except now I'm calling the standard deviation a sample standard deviation, because both of these values came from our sample. So we don't know the population standard deviation. So we know n is 40, x bar is 85, s is 10. Now we want 95% confidence. Okay. Now, if sigma is unknown, this is where we use the table to look up the value. And that depends on two things. It depends on the level of confidence and our degrees of freedom. If n is equal to 40, then what is our degrees of freedom? Do you remember how we found that? N minus 1, and so in this case it would be 39. Alright. So we want to go to our table and look up this value for T alpha over 2. So 95% confidence and 39 is our degrees of freedom. Now 95, that's our middle column right here, right down the middle. So we go down to 39 and go over to the middle, and we see a value of 2.023. Right here. Can y'all see that okay on your screen? Could make it's about as big as I can make it. Well, actually, I take that back. I can go a little bit larger. Yeah, so 39, and we go across, and then here's 2.023. So I'll write that down real quick. Okay. Let's go back. All right. So from our table, we got 2.023 for T alpha over 2. So our error term is T alpha over 2 times S divided by square root of n, not 10, n. I was looking at S for some reason. Then we fill in those values, 2.023 times 10 over the square root of 40. And again, this is just a matter of calculation. 2.023 times 10 divided by square root 40. That looks to be about 3.2. Okay, so that's our error term, 3.2. Let me make a quick comparison. So notice we just worked this problem. Oh, it's on the back of this page, I'm sorry. When we worked this problem, 95% confident, and we knew that 10 was the population standard deviation, it gave us an error term of the back of this, and it's upside down. It gave us an error term of 3.1. And this time, same level of confidence, but now knowing that we have a sample standard deviation instead of a population, we got a higher error value in 3.2. Not a lot higher, but higher nonetheless. And that's generally what happens if everything else is considered equal. If we go from knowing the population standard deviation to only knowing the sample standard deviation, what happens is it creates more uncertainty, and so we're going to end up with a larger error term as a result. And so that's exactly what's happened here. We went from 3.1 when we had mu to 3.2 when we only had s. So s is we're not going to be able to be as confident with a sample value versus a population value, and hopefully that makes a lot of sense to you. And because we don't have that population level data, it's going to create more uncertainty, like I said. Okay. Well, let me. Let's go ahead and create the confidence interval before we finish here. So it's still x bar minus e, x bar plus e, and so that'll be 85 minus 3.2, 85 plus 3.2. So that is 81.8 to 88.2. Let's say 8 again, that's not right. 88.2. So we are 95% confident that the mean is between these two values. Okay. Okay, let's look at an actual problem here. One that has context as well as numbers. Okay, this is number 30 on page 445. A recent Gallup poll asked 1,006 Americans during the past year about how many books, either hardcover or paperback, did you read either all or part of the way through? Results of the survey indicated that X bar was equal to 13.4 books and the standard deviation S was equal to 16.6 books. Construct a 99% confidence interval for the mean number of books that Americans read either all or part of during the preceding year, and interpret the interval. Whenever it says interpret, that means write a sentence describing what actually has happened, and we'll be able to write a little bit more descriptive sentence this time since we have context. So the poll asked 1,006 Americans during the past year how many books, either hardcover or paperback, did you read either all or part of the way through. So we got X bar is 13.4 and S is 16.6. Now, Notice in this problem, and well, you may not notice. Let me show you. In the question, it actually says S equals 16.6. That's pretty generous of them because they just told us this is the sample standard deviation. Okay. Sometimes you'll have to, kind of figure out what they're asking. If you look at the problem above, it says the mean number is that with the standard deviation of that. Now, it doesn't necessarily say that that's either a population standard deviation or a sample standard deviation. So we really should, in that case, assume it's a sample if we're not told otherwise. And that's probably the safest way to proceed because that'll give us it'll end up with a little bit larger margin of error, but that's us playing it safe. Better to have too large than too small of a margin of error. Okay, and I didn't write down one other key thing, which was we have 99% confidence. Now, because we're given S and not sigma, sigma is unknown, we have to have degrees of freedom. What are the degrees of freedom for this particular problem? (1005). Okay, so based on that, we can calculate T alpha over 2. But again, let's go to our table. Now, 99% confidence is right here, first column. So we go down to 1005 degrees of freedom. We get down here, we don't really have a 1005. What do you think we ought to use for our degrees of freedom, since 1005 is not specifically listed? (1000), exactly. Since it's the closest value to the one that we have. Yeah. And that's what they really intend. After we get to 40, they start, they have 45, 50, then they start counting by 10s up to 100, and then they start counting by 100s up to 500, 1,000, 2,000, and large. Because you see the numbers are not really changing that much at that point anyway, so there's not a whole lot of need to write all the numbers in between. There's actually a lot of change happening here at this level as we increment it by 1, but by the time we get to this size, there's not as much difference between these values, which is why they don't list all the numbers over here that we see previously. So we can use 2.581 for 1,000. Okay. So we have that. We have 2.581 now. So we calculate E, which is T alpha over 2 times S divided by square root of N. So 2.581 times 16.6 divided by the square root of 1005. Okay. So we can say E, let's say it's equal to 1.35. These are already to the first decimal place, so I'll just round these to the second decimal place. We could say 1.4, but since 5 is right in the middle, I have a hard time rounding that either to 3 or the 4. So I would go ahead and just go to that next place, so 1.35. Alright, so now we just need x bar minus e and x bar plus e. So that'll be 13.4 minus 1.35, comma, 13.4 plus 1.35. Which gives us, let's see, that would be 12.05, comma, 14.75. Okay, and now to summarize, you can say we are 99% confident that the mean number of books Americans read all or part of last year is between 12.05 and 14.75. Okay. This time, because we actually knew what the question was asking us about, it wasn't just generic numbers thrown at us that I made up. Now we can actually include in our sentence here what it is that we're talking about, which is the mean number of books that Americans read all or part of last year. Okay, so it's important that we provide the context in this sentence. That way we can convey exactly what we've found in this confidence interval. What does this confidence interval represent? This is our interpretation now. Anyway, are there any questions on this? Okay. Let's look at this review real quick. I'll go back up to the top. I wonder if that's too big. That's probably alright. So, you may have noticed if you look in the file folder, the title of the review, I don't know if you can see it here. You can't see it here. The title of the review is Test 3 Review dash skip number 7. I didn't feel like editing out number 7. That's the problem I skipped from section 9.1 that we would have otherwise done given a little bit more time. So just skip problem 7 in the review. We didn't even look at how to do that, so we're going to go over the review in class next week, Monday and Tuesday, on those respective classes. So you don't necessarily have to work through this if you don't have time, but I do encourage you to give these a shot just to see where you're at individually, so that when we go over them as a group, you can kind of see how well you've done with the review, or if there's certain areas that you need to improve. So, problem 1 and 2 both use the same setup, which I think we did that in. I think I did this in class as an example. But this is 7.2, so it's less than a certain x value, and then between two different x values. Remember, we always need two different z-scores. Third problem, determine the 90th percentile, so that's an inverse normal calculation. I don't know why I left all that space for this. It's a short problem. Now, problem 4 and 5 are both with this. This time we have a sample of 36 individuals, so this is an 8.1 question. Talking about central limit theorem, and we have a little bit different z-score calculation as a result because of that. This one's less than, this one's greater than. And then problem 6, this is from our lecture earlier this week on section 8.2, which was the sample proportions and things like that. I didn't phrase that as best as I could. Anyway, but this is our p-value, our population proportion, and then we can use these two numbers here, 65 and 205. We can calculate p-hat based on that. And then I kind of lead you through all the steps, show the distribution is approximately normally distributed. What I've decided is that I'm not going to have you check the other condition, that n is less than or equal to 0.05 capital N. We'll be okay with that. So this is just n times p times 1 minus p is greater than or equal to 10. Calculate p-hat. Find the probability that p-hat is greater than the value in part B by first calculating the standard deviation and then the z-score. So basically leading through the steps. 7, we didn't talk about how to do this, so skip it entirely. And then 8 and 9 are both from today's lecture on confidence intervals. This first one, notice it says a population standard deviation, so we know what sigma is, and we can use the z alpha over 2. And then this one, we know that we're given a sample standard deviation, so we'll use the t alpha over 2 and the degrees of freedom, and we use that table to generate the t alpha over 2 value here. And then here's a formula page. And then our t distribution table, like I told you. And that's all we really need there. Everything else is... and now on the formula page, I've also included calculator instructions to an extent. Now the instructions I've given you here are for the 83 specifically, 83 and 84. But this is specifically the 83. So I may edit this a bit and create one for the 36s also. So anyway, so we will stop there for today. We're out of time anyway. So you all have a good rest of the day, have a good weekend, and we will go over this review next week. Take care. Bye. You too.